Welcome back to the deep dive. Have you ever found yourself wondering how doctors can peer inside your body without surgery? Or maybe why, even though lightning and thunder happen at the same instant, we always see the flash before we hear the boom? Well, these everyday marvels are actually deeply rooted in the physics of sound. Today, we're taking a crucial deep dive into this fascinating world of sound. It's not just fundamental for understanding the world, but it's also a really vital topic that pops up frequently in competitive exams. We're talking UPSC, SSC, state PSCs, and yeah, even your class 9th to 12th board exams. So our mission in this deep dive is to really unpack how sound works, how it's made, how it travels, what makes sounds different, and some of its pretty surprising uses. Let's get started.
Okay, so to begin, let's think about sound not just as noise, but actually as a form of energy. It's the energy that produces the sensation of hearing in our ears. And just like other forms of energy, think mechanical energy when you clap, or light energy, sound follows the law of conservation of energy. It can't be created or destroyed, it just changes form. So that clap, that's mechanical energy turning into sound energy.
Changing form, right? Not appearing out of nowhere.
Exactly. But here's the really fundamental part. Every single sound, every sound, starts with one simple thing: vibration. Think about a tuning fork. You strike it, maybe on a rubber pad, and the prongs kind of shimmer, right?
Yeah, you can see them moving.
That shimmer is the vibration, and that's what makes the sound. You can even feel it if you gently touch a vibrating prong. Or try this if you bring a vibrating tuning fork close to, say, a table tennis ball hanging on a thread.
Oh, push it away.
Precisely. The ball gets visibly pushed. It's direct proof of that physical vibration. Even dipping a vibrating fork into water, you see ripples, splashes. Again, it clearly shows the link between that back and forth movement and the sound.
Huh. It seems so simple when you put it like that. Vibration equals sound.
It is, at its core. And it's everywhere. Our own vocal cords vibrate when we speak. Pluck a stretched rubber band, it vibrates, makes a sound. A bee buzzing, that's its wings vibrating incredibly fast. And every musical instrument, from a violin string to the air inside a shinai, makes sound because something specific is vibrating. Strings, air columns, membranes. Something's moving back and forth.
So vibration is the absolute essential starting point. That's a key concept. Okay, so
Yeah.
once that vibration happens, how does the sound actually get from that vibrating object, the tuning fork or the guitar string, to our ear?
Right, that's the next logical step. We know vibrations produce sound, but for us to hear it, that sound needs a pathway. It needs a medium to travel through.
A medium, like air.
Exactly. Air is the most common one. But it could also be a solid or a liquid. What happens is, when an object vibrates, it literally nudges the particles of the medium right next to it. These particles then bump into their neighbors and pass the disturbance along. Now, here's a crucial point. The particles themselves don't travel all the way from the source to your ear. No.
They don't.
No, they just oscillate. They wiggle back and forth around their original equilibrium positions. It's the disturbance that moves forward. Think of it like doing the wave in a stadium. People move up and down, but the wave travels around.
Okay. So it's the energy, the disturbance that's propagating.
Precisely. And this traveling disturbance, where particles set their neighbors into motion, that's what we define as a wave. So we can clearly picture sound as a wave. And because these sound waves absolutely need a material medium, something tangible for the particles to interact with, they're classified as mechanical waves.
Mechanical waves,
Yeah.
because they involve the mechanics of the medium's particles.
Exactly. And air, as we said, is the most common medium. So when a vibrating object, let's say a speaker cone, moves forward, it pushes the air molecules in front of it together. It squeezes
Well,
them.
right. Compressing them.
Yes, creating a region of high pressure. We call this a compression, often labeled C. Then, as the object moves backward, it pulls away, creating space.
Leaving a gap.
Sort of. It creates a region of low pressure where the molecules are spread further apart. This is called a rarefaction, labeled R. And as the object vibrates rapidly back and forth, it sends out this continuous series of compressions and rarefactions rippling through the air.
Like pulses of high and low pressure.
Exactly. These variations in pressure and density travel through the medium as the sound wave.
That's a fantastic explanation of propagation, and it really highlights the need for a medium. So that brings up that classic question. If sound needs something to travel through, why couldn't you and a friend hear each other if you were, say, standing on the moon, even if you shouted?
Perfect example. The moon has virtually no atmosphere.
Yeah.
There's no air, no gas, no medium for those compressions and rarefactions to form and travel through.
So silence.
Complete silence.
Yeah.
It really hammers home that sound needs that material connection to propagate. Now, digging a bit deeper into how these waves move, sound waves are specifically known as longitudinal waves.
Longitudinal. Okay, what does that mean exactly?
It means that the individual particles of the medium, the air molecules, for instance, move back and forth in a direction that is parallel to the direction the wave itself is traveling.
Oh, okay.
Think of a slinky toy. If you stretch it out along the floor and give one end a sharp push forward,
You see a pulse travel down it.
right, a compression travels along the slinky. Now, if you put a little mark on one single coil of that slinky, what does it do?
It just moves forward and back along the line of the slinky?
Exactly. It moves back and forth, parallel to the direction the compression is traveling. That's precisely how sound works. The air particles oscillate, they wiggle, parallel to the direction the sound energy is moving.
Got it. So the wiggling is in the same direction as the wave's journey.
Correct. And this is different from, say, transverse waves.
How are they different?
In transverse waves, the particles oscillate perpendicular at right angles to the direction the wave is traveling. Think about making waves on a rope by shaking one end up and down. The wave travels along the rope, but the parts of the rope move up and down.
Or waves on water, like you mentioned. The water goes up and down, but the wave spreads outwards.
Perfect examples. Light, interestingly, is a transverse wave. But, and this is important, light is not a mechanical wave. It doesn't need a medium. It can travel through the vacuum of space. Sound can't.
That slinky analogy really helps visualize the longitudinal part. So sound waves are mechanical and longitudinal. Key takeaway.
Definitely. And when we want to describe a specific sound wave, we use several key characteristics. These are crucial.
Okay, what are they?
We mainly talk about frequency, amplitude, and speed. Let's start with frequency, often shown by the Greek letter nu. Frequency tells us how often something happens. For a sound wave, it's the number of complete oscillations, one compression and one rarefaction cycle that pass a fixed point in 1 second. Its SI unit is the hertz, named after Heinrich Hertz, a brilliant physicist.
Hertz, right. We see that often.
And our brain interprets frequency as pitch. Higher frequency means higher pitch. Lower frequency, lower pitch.
So a flute playing a high note has a higher frequency than a tuba playing a low note.
Exactly. The flute sound wave has more compressions and rarefactions passing by each second. Think of a high pitch like a squeak and a low pitch like a rumble. Closely related is the time period t. This is just the time it takes for one complete oscillation to happen. Its unit is the second s. And frequency and time period are simply inverses, equals 1t. If the frequency is high, the time period is short, and vice versa.
Makes sense. Faster oscillations take less time each.
Precisely. Now, amplitude A. Amplitude is about the size or intensity of the wave. Technically, it's the maximum displacement or disturbance of the medium's particles from their normal resting position. For sound, its unit relates to pressure or density.
And what does amplitude tell us about the sound we hear?
Amplitude primarily determines the loudness or softness of the sound. A larger amplitude means a louder sound.
Why louder?
Because a larger amplitude wave carries more energy. It causes a bigger disturbance, a stronger sensation in our ears. Think about hitting a drum softly versus hitting it hard.
Hitting it harder makes a louder sound.
Right, because you've created a wave with a larger amplitude, it has more energy. Now, it's useful to quickly distinguish between loudness and intensity here. Loudness is subjective. It's how our ears and brain perceive the sound. Intensity, on the other hand, is an objective physical measure. It's the amount of sound energy passing through a unit area per second. They're related, but not exactly the same.
Okay, so amplitude links mainly to loudness. What else?
Then we have wavelength, symbol lambda. This is the actual physical distance between two consecutive identical points on the wave. So the distance from one compression peak to the next compression peak, or from one rarefaction trough to the next. Its SI unit is the meter, m.
Okay, frequency, amplitude, wavelength. What was the last one?
Speed, v. This is simply how fast the wave specifically, a point on the wave like a compression peak, travels through the medium, distance per unit time. And these three, speed, wavelength, and frequency, are beautifully related by a fundamental equation. V equals this.
Speed equals wavelength times frequency. That seems really important.
It is. It connects the spatial aspect, wavelength, with the temporal aspect, frequency, to determine the speed. And an interesting point. The speed of sound in a given medium under constant conditions like temperature is generally the same for all frequencies. Bass notes and treble notes travel at the same speed through the same air.
That's useful to know. So could we use that equation to solve a problem?
Absolutely. Let's try one. Imagine a sound wave has a frequency of 2 kilohertz, which is 2,000 hertz, and its wavelength is 35 centimeters. How long would it take for this sound to travel 1.5 kilometers?
Okay, let's see. Frequency equal 2,000 hertz. Wavelength equals 35 centimeters. We should convert that to meters, right? So 0.35 meters.
Good. First step is to find the speed, using V equals cell.
So V equals 0.35 meters times 2,000 hertz. That's 700 meters per second. Is that right?
Perfect. The speed of the sound wave is 700 meters.
Now we need the time to travel 1.5 kilometers, which is 1,500 meters. Time is distance speed.
Exactly.
So time equals 1,500 meters, 700 meters. Okay, calculator. Roughly 2.14 seconds.
Precisely. So it'd take about 2.1 seconds for that specific sound wave to travel 1.5 kilometers.
Yeah.
See how the characteristics work together.
Yeah, that makes it very concrete. Are there any other characteristics?
There's one more, often called quality or timbre. This is a bit more subtle. Timbre is what allows us to distinguish between two different sounds, even if they have the same pitch, frequency, and the same loudness, amplitude.
How does that work? Like telling a violin and a piano apart when they play the same note at the same volume.
Exactly like that. A sound with just one single frequency is called a pure tone, like a tuning fork produces. But most sounds, especially from musical instruments or voices, are actually a mixture of a fundamental frequency and several other higher frequencies called overtones or harmonics. This complex mixture gives the sound its unique flavor or timbre. A blend of frequencies that sounds pleasant is often called a note.
And unpleasant sounds.
We generally call those noise. Noise is typically a jumble of frequencies without a clear, pleasant harmonic structure.
Okay, that distinction between tone, note, and noise based on frequency mix is interesting. So, mastering frequency, amplitude, speed, wavelength, and timbre really forms the bedrock for understanding sound waves. Crucial for exams too, I bet.
Absolutely foundational. And speaking of how sound behaves, let's talk more about its speed. As we noted, sound travels at a finite speed. It's fast, but much, much slower than the speed of light.
Which brings us back to lightning and thunder.
Exactly. Light travels so incredibly fast, about 300 million meters per second, that we see the lightning flash almost instantaneously. Sound, traveling through air at maybe 340-ish meters per second, takes noticeable time to reach us from the lightning strike, hence the delay.
Right. And you mentioned speed depends on the medium.
Yes, primarily on the properties of the medium itself and also its temperature. Generally, sound travels fastest in solids, slower in liquids, and slowest in gases.
Why is that?
It's mainly about how closely packed the particles are and how strongly they interact. In solids, particles are very close and tightly bound, so vibrations get passed along much more quickly and efficiently. In gases, particles are far apart and interact less, so it's a slower process.
Can you give some examples of speeds?
Sure, at a standard temperature like 25 degrees Celsius, the speed of sound in, say, aluminum, a solid, is around 6,420 meters, really fast. In distilled water, a liquid, it's about 1,498 meters, and in air, a gas, it's only about 346 meters at that temperature. See the huge difference?
Wow, yeah. Over 10 times faster in aluminum than in air.
And temperature matters too. As the temperature of the medium goes up, the particles have more energy, move faster, collide more often.
So the sound travels faster.
Generally, yes. For example, in air, the speed is about 331 meters at 0 degrees C, but it increases to around 344 meters at 22 degrees C.
That difference in speeds across media explains something I've heard about trains.
Putting your ear to the rail.
Exactly. You can hear the train coming through the solid steel rail much sooner than you hear it through the air.
Perfect real-world example. The sound travels much faster through the solid steel. Now, another behavior sound shares with light is reflection.
Bouncing off surfaces.
Precisely. When a sound wave hits a boundary, like a wall or even the surface of a lake, it bounces back. And it follows the same basic laws of reflection that light does.
Which are?
Two main laws. First, the incident sound wave coming in, the reflected sound wave going out, and the normal, that imaginary line perpendicular to the surface right where the sound hits, all lie in the same flat plane. Second, the angle of incidence, the angle between the incoming sound and the normal, is equal to the angle of reflection, the angle between the outgoing sound and the normal. Angle in equals angle out.
Just like light bouncing off a mirror, does the surface need to be smooth?
For effective reflection, you generally need a large obstacle compared to the wavelength of the sound. Interestingly, unlike light, the surface doesn't need to be optically polished. Even rough surfaces like walls or cliffs reflect sound quite well.
And the most famous example of sound reflection is?
An echo. Absolutely.
Yeah.
If you shout or clap near a suitable reflecting surface, a tall building, a cliff face, a mountainside, You'll hear the sound come back to you a little later.
That's the reflected sound wave reaching your ears after the original sound.
Exactly. Now, for our brain to perceive the reflected sound as a separate, distinct echo, there needs to be a minimum time gap between the original sound and the echo,
How long?
generally accepted to be about 0.1 seconds. Our hearing persistence is about that long. So if the speed of sound in air is, say, 344 meters at around 22 degrees C, in that 0.1 seconds, the sound has to travel to the obstacle and back.
So the total distance traveled is speed x time. 344 meters times 11s equals 34.4 meters.
Right, that's the total round-trip distance. Which means, for you to hear a distinct echo, the reflecting obstacle must be at least half that distance away from you.
Half of 34.4 meters. 17.2 meters, roughly 56 feet.
That's the minimum distance, yes. And remember, this distance will change slightly if the temperature, and thus the speed of sound, changes. Sometimes, if sound reflects off multiple surfaces, you can hear a series of echoes, like the rolling sound of thunder, which is caused by multiple reflections between clouds and the ground.
Can we try applying that echo calculation?
Sure, let's say a person clapped their hands near a cliff and heard the echo exactly 2 seconds later. If the speed of sound that day was 346 meters, how far away is the cliff?
Okay, time delay is 2 seconds. Speed is 346 meters. The total distance the sound traveled is speed x. Time equals 346 meters. 82x equals 692 meters.
Good, that's the round trip.
So the distance to the cliff is just half of that. 692 meters equals 346 meters.
Exactly right. The cliff is 346 meters away.
Okay. Echoes are distinct reflections. What about inside a large room, like an auditorium? Sometimes the sound seems to linger.
Ah, that's a related but different phenomenon called reverberation. In an enclosed space, sound waves reflect repeatedly off the walls, ceiling, floor, everything. These multiple reflections blend together. Instead of hearing distinct echoes, you hear the sound persisting, gradually fading away as its energy is absorbed by the surfaces in the air. This persistence is reverberation.
And is that good or bad?
Well, a little reverberation can make music sound richer, fuller, but too much reverberation is definitely undesirable, especially in places like lecture halls or auditoriums. Because the lingering sounds of earlier words or notes blur into the new ones, making speech unclear and music muddy. It reduces intelligibility.
So how do they control it?
By using materials that absorb sound rather than reflect it well. Things like acoustic tiles on the ceiling, heavy curtains or draperies, carpets, even the audience members themselves help absorb sound energy and reduce reverberation time. Materials like compressed fiberboard or rough plaster are often used.
So architects and sound engineers have to carefully manage reflections.
Absolutely. And they also harness reflections deliberately. There are many practical uses of multiple reflection of sound.
Like what?
Think about megaphones or loudhailers or the flared bells of musical instruments like trumpets or horns, even the shinai.
They're all shaped like cones or funnels.
Yes, and that shape is designed to guide the sound waves through successive reflections, concentrating them and directing them forward in a specific direction, preventing the sound from just spreading out wastefully in all directions. Makes the sound louder in that direction.
Clever. What else?
The stethoscope, a doctor's best friend. It uses multiple reflections inside its narrow tubes to channel the faint sounds of a patient's heartbeat or breathing directly and efficiently to the doctor's ears.
Ah, I never thought about the reflections inside the tube.
And consider large concert halls or even some cinema halls. Have you ever noticed the ceilings are often curved? Or there might be large curved panels called soundboards behind the stage.
Yes, I have seen those.
That curvature isn't just decorative. It's carefully designed so that sound reflecting off it spreads out evenly across the entire hall. It helps ensure everyone in the audience gets a good, clear sound, distributing the reflected sound energy effectively.
It's amazing how these basic physics principles are engineered into so many things we encounter. These applications definitely seem like prime exam material.
They often are. Now let's shift gears slightly and talk about the range of hearing. What frequencies can we actually hear? For an average, healthy young human, the audible range is generally considered to be from about 20 hertz on the low end up to about 20,000 hertz or 20 kilohertz on the high end.
20 hertz to 20 kilohertz, that's quite a wide range, but is that all the sound there is?
Not at all. There's a whole world of sound outside our range. Sounds with frequencies below 20 hertz are called infrasonic sound, or simply infrasound.
Below our hearing threshold, can anything hear or use it?
Oh yes. Rhinoceroses, for example, communicate using infrasound frequencies as low as 5 hertz. Whales and elephants also produce and likely perceive infrasound, possibly for long-distance communication. And interestingly, earthquakes generate low-frequency infrasound before the main shock waves arrive. Some researchers believe this might be what alerts certain animals, allowing them to react before humans feel the quake.
Fascinating. So that's below 20 hertz. What about above 20 kilohertz?
Frequencies higher than 20 kilohertz are called ultrasonic sound or ultrasound.
And animals use this too.
Extensively. Dolphins, bats, porpoises, they are masters of ultrasound. They use it for echolocation, emitting ultrasonic pulses and interpreting the echoes that bounce back to navigate and hunt, even in complete darkness or murky water.
Like sonar, but biological.
Exactly. And some prey have adapted too. Certain moths have evolved highly sensitive hearings, specifically to detect the ultrasound cries of bats, giving them a chance to take evasive action.
An evolutionary arms race in sound. Can any humans hear ultrasound?
Generally, no, although young children, maybe under 5, and some animals like dogs, can often hear frequencies slightly higher than 20 kilohertz, perhaps up to 25 kilohertz. And for people who have difficulty hearing within the normal range, technology steps in. A hearing aid is essentially a miniature sound amplification system. It uses a microphone to pick up sound, converts it to electrical signals, amplifies these signals electronically, and then a tiny speaker converts the amplified signals back into sound waves delivered to the ear. It's battery-operated and a lifesaver for many.
It's incredible to think about these sound frequencies beyond our perception, infrasound and ultrasound, being used so actively in the natural world. It really broadens the picture.
It certainly does. In ultrasound, those high-frequency waves aren't just for bats and dolphins. They have incredibly important applications in industry and medicine.
Why ultrasound specifically? What makes it useful?
Because they are high frequency, they have short wavelengths. This means they can travel in very well-defined, narrow beams, almost like a spotlight of sound, and they don't spread out or bend around obstacles as much as lower frequency sound does. They also carry significant energy.
Okay, so how is that used in industry?
One common use is for cleaning, especially for small, intricate parts or things with hard-to-reach areas like spiral tubes, odd-shaped machinery, or delicate electronic components. You place the objects in a cleaning solution and then blast ultrasonic waves through the liquid. These high-frequency vibrations create intense agitation and tiny cavitation bubbles that effectively scrub away dust, grease, and dirt particles from all surfaces.
It's like a microscopic power washing.
That's a good way to think of it. Another really critical industrial application is detecting flaws in metal blocks or welds, especially in large structures like bridges, airplanes, or machine parts where safety is paramount. Ultrasonic waves are sent into the metal block. Detectors are placed to pick up the waves that pass through. If there's an internal crack, void, or flaw, the ultrasound waves will be reflected back or scattered by the defect instead of passing straight through.
So the detectors notice a weak spot or no signal.
Exactly. It indicates a hidden flaw. Ordinary, lower frequency sound waves wouldn't work well because their longer wavelengths would just bend around small defects, missing them. Ultrasound short wavelength gives much higher resolution for finding these flaws.
That's incredibly important for safety and quality control. What about medical uses? We hear about ultrasound scans all the time.
Yes, medical applications are vast. Echocardiography uses ultrasound pulses directed at the heart. The waves reflect differently from the heart valves, chambers, and muscle walls. These reflected echoes are detected and used to build up a moving image of the heart, allowing doctors to assess its function and diagnose problems.
Seeing the heart beat in real time, amazing.
Then there's general ultrasonography. This uses an ultrasound scanner, a transducer that emits pulses and detects echoes to create images of various internal organs. Doctors use it routinely to look at the liver, gallbladder, kidneys, uterus, bladder, and other structures. It's invaluable for detecting things like gallstones, kidney stones, tumors, or other abnormalities.
And of course, in pregnancy.
Yes, perhaps its most well-known use is for examining the fetus during pregnancy. It allows doctors to monitor the baby's growth, check development, detect potential congenital defects, and assess the overall health of the pregnancy, all without using potentially harmful X-rays. The scanner sends pulses, receives the echoes bouncing off the fetus and surrounding structures, and a computer converts these signals into the images we see on the screen.
It's a non-invasive window into the body. Are there other medical uses?
One more significant one is using focused high-intensity ultrasound to break kidney stones. Instead of surgery, powerful ultrasonic pulses can be directed precisely at small kidney stones. The intense vibrations break the stones down into tiny, sand-like grains.
Which can then be passed naturally.
Exactly. The fine grains can then be flushed out of the body with urine, often avoiding the need for more invasive procedures.
These applications are truly remarkable. From cleaning tiny parts to seeing inside the human body and even performing non-invasive treatments, it really shows the power locked within understanding these high-frequency sound waves. Well, as we start to wrap up this deep dive, let's just take a moment to maybe recap the core insights we've covered today.
Absolutely. We started right at the beginning, didn't we? Establishing that sound fundamentally originates from vibrations. We saw how it propagates as a longitudinal mechanical wave through a medium characterized by those traveling compressions and rarefactions. Then we explored its key characteristics: frequency determining pitch, amplitude determining loudness, along with wavelength, time period, and speed, and how they're connected by V equals E. We also touched upon timbre, or quality.
And the speed isn't constant everywhere.
Right, we saw how the speed of sound varies significantly, depending on the medium, fastest in solids, slowest in gases, and also on temperature. We looked at reflection of sound, leading to phenomena like echoes, requiring a minimum distance related to sound speed and hearing persistence,
Yeah.
and reverberation, the persistence of sound in closed spaces.
Plus the practical uses of those reflections.
Yes, the clever designs of megaphones, stethoscopes, and concert halls, harnessing multiple reflections. We then expanded beyond human hearing, discussing the ranges of infrasound, below 20 Hz, and ultrasound, above 20 kHz, used by various animals. And finally, we dove into the remarkable applications of ultrasound, from industrial cleaning and flaw detection to vital medical diagnostics like echocardiography and ultrasonography, and even therapeutic uses like breaking kidney stones.
It's been a comprehensive journey through the world of sound, and it really is vast and constantly evolving. I really encourage you, our listeners, to keep observing the soundscape around you. Think about these principles. How are they playing out when you hear music, or listen to someone speak, or even hear a distant siren? Your consistent effort in really grasping these concepts won't just deepen your understanding, it will definitely set you up for success in your examinations. Stay tuned for more exam-ready insights and subscribe to never miss a topic breakdown. In this episode, we covered the following topics. What is sound and how it is produced? In this episode, we covered the following topics. Propagation of sound and mechanical waves. In this episode, we covered the following topics. Longitudinal nature of sound waves. Characteristics of a sound wave. Frequency, amplitude, wavelength, time period, and speed. Characteristics of a sound wave. Speed of sound in different media. Reflection of sound. Echo and reverberation. Reflection of sound. Uses of multiple reflection of sound. Range of human hearing. Infrasound and ultrasound. Range of human hearing. Applications.